Hello, in this video we're going to look at antiderivatives and integrals. This is a little bit more math heavy than before, but what we want to do is straighten out transforming from, say, a velocity graph to a position graph or a displacement graph, and that's exactly the example we'll do. So we have dx dt is equal to v, and technically that's a differential equation. Very easy one, but still a differential equation. And the way you solve this kind of differential equation is you separate it. It's called a separable differential equation. So you separate the x from the t. You put one on one side, one on the other, and then you integrate it. Now when you integrate, you have two choices. You can do a definite integral or an indefinite integral. Let's start out doing an indefinite integral. So when you do that, you get this unknown constant c. Technically, you get one constant from each integration, but we can combine those unknown constants into just one unknown, which we'll call c. And we want to figure out what that is. In an earlier video, I said that this is going to be equal to the initial position, x initial. Well, let's prove that that's the case. So on the left-hand side, we would get x, and on the right-hand side, we're left with integral v dt plus c. So x as a function of time would be equal to this integral over here as we go from t initial to t final. Let's say that t initial, we'll call that t naught, and t final we'll just call t. Then we have v dt plus some unknown constant. So a reminder, what are our limits here? Well, we're going from initial time to final time. That's how we get a displacement after all. Okay, so with that, what would x at t initial be? Well, x at t initial would be equal to the integral t initial to t initial v dt plus c. Well, that's got to be 0. If you have an integral and the limits are the same, there can't be, that's always 0 by definition. So you can't have any area under that curve. Okay, so that means that x at t initial is equal to c, and x at t initial is equal to x initial by definition. I'll use this abbreviation here for definition. Okay, so that tells us then that x as a function of t must be equal to the integral from t initial to t v dt plus x initial. All right, now there's another way to do this. So, what we can do is a definite integral. So we start back at the same starting point. Dx is equal to v dt. And we do a definite integral. When you do a definite integral, you have to give your integral's limits. So what limits would go with an x? Well, we'd have an initial x and a final x. And then likewise, what limits go with time? Well, initial time and final time. And we don't have any extra unknown constant because this is a definite integral. All right, on the left-hand side, we're going to get x minus x initial after we integrate. And on the right-hand side, we don't know what this function v is, so we'll just leave it as an integral. And that tells us that x is equal to the integral from t initial to t v dt plus x initial, the same answer that we had before. So it's a little bit quicker this way, and so it's just a matter of taste. Personally, I like the quick way, but either way. So this shows us how we undo the derivative. Integration undoes derivatives. Integration is an antiderivative. So that's what I was talking about in the previous video. All right, until next time.